Hey guys, today's video is about association mining. We'll only discuss chi-square test today. You can find the others in my channel. Chi-square test is used to measure the correlation between two nominal attributes. The attributes have to be nominal, otherwise the result would be meaningless. In data type video we've discussed, binary attribute is just a special case of nominal with only two states. In terms of transactions, we can apply the binary concept. The two scenarios are whether all the items are present in a transaction or not. Before looking at the formula, I want to introduce some symbols. A and B are two nominal attributes, and their states are denoted by A1, A2 to AI, B1, B2 to BJ. For example, A is the hair color, so A1 may be black, A2 may be red. If we have 5 colors, then A contains states A1, A2 to A5. Then, N is the total number of transactions in a database. The formula is like this. It looks complicated, but the calculation is actually not that scary. OLK is the observed frequency of states A, L, and BK. The observed frequency means these incidents are stored in our database because we indeed observe them in the real world. ELK is the expected frequency of states AL and BK. This expected frequency is what we would expect under the independence assumption, not always the real-world situation. So there is some calculation involved. The expected frequency is the product of the count of AL and the count of BK divided by the total number of transactions. In fact, this formula only contains these two variables, OLK and ELK, so it's not so difficult. Let's look at an example. The thing I didn't talk about before is the summation symbols in the front. It basically means we have to iterate all the possibilities or combinations, so the calculation may be a little annoying. We have database like this, and this is a contingency table. To illustrate, the 5 here means there are 5 transactions in our database contains both A and B. The 3 here means there are 3 transactions which contains A but not B. The 20 means the total number of transactions because we sum up all the observations. Okay, the summation in the formula means we have to calculate the number for each position in this yellow box. So we have to do calculation 4 times. As an example, I will first show you how to calculate the 5 on top left corner. OLK is just 5 because we observe 5 transactions containing both A and B. ELK is the count of A times the count of B divided by N. We start with the simplest. N is the total number of transactions, so it's 20. Then, the count of A is 8. We count the number of transactions containing A, irrespective of other variables. It's like a marginal count. We only care about whether a transaction contains A. Similarly, the count of B is 15, which is the number of transactions contains B. Then, we have the answer, 8 times 15 divided by 20. Which is 6. So, the observed frequency is 5, and the expected frequency is 6. Basically, we just repeat this process for each position. You can pause the video now and try to figure it out, but I'll do the calculation one more time. So we now look at the top right corner, which corresponds to the transactions containing B but not A. To begin with, OLK is 10. Because we observe 10 transactions that fit the condition. Then, ELK is the count of the absence of A times the count of B divided by N. N is 20, just the total number of transactions. Count of the absence of A is 12, which is the column summation. The count of B is 15, which is the row summation. So, the expected frequency is 12 times 15 divided by 20, which is 9. For this particular position, the observed frequency is 10 and the expected frequency is 9. I hope you now see the calculation is not difficult, but you have to repeat the process many times. The last step is to plug in the observed and expected frequencies into formula. Here's the answer we got. The chi-square statistics for this dataset is 1.111. So, what does this number mean? We start with the simplest scenario. When chi-square is 0, A and B are perfectly independent. It's because the numerator is the square of observed frequency minus the expected frequency. The only way for this number to be 0 is that the observed is equal to the expected frequency. Expected frequency is calculated under the assumption of independence. So, when chi-square is 0, A and B must be independent. If chi-square is not equal to 0, you can define a threshold and find the corresponding number in chi-square table, then determine whether the correlation should be considered interesting or not. But that kind of operation involves some statistics background. Typically, when chi-square is larger than 1, we consider the correlation interesting. From the example before, we have chi-square 1.111. So we believe A and B are correlated to some degree, and we might want to do further research. One last thing I want to remind you is that we can't tell the direction of correlation from chi-square statistics. That is, we don't know whether two variables are positively or negatively correlated. We only know they are strongly correlated. This is because in a formula, we take the square in the numerator to avoid the problem of offset. However, other statistics can tell us about the direction of relationship, such as lift. Therefore, we always need multiple tools to make a justifiable decision. So, that's the basic idea of chi-square test. Thank you for watching my video and see you soon.